Alright, ladies and gentlemen, and everybody else, we are on to our next example. I'll try to speed up the process a bit. We've done like 2 examples now in a very sort of slow pedestrian way. Let's work out the next one a little bit faster, hopefully, if I can keep it up. And you can always fill in the details because you now understand Gauss's law. So the example now is an infinite sheet of charge with a certain surface charge density, meaning every, say, square meter of the sheet has 2 coulombs. So depending how many square meters you get, that determines the number of coulombs you're going to get. And we want to figure out the electric field a certain height above the sheet. Now this should be a vertical line upwards. It's kind of, you really have to think in 3D here, right? This is my sheet. It's like flat. If this actual piece of paper is the sheet, I want to figure out the electric field up here, where the tip of my pencil is, for example. So a certain height h above that surface. And I'm going to imagine this sheet is infinite. I can't draw an infinite sheet. I can't even draw part of an infinite sheet. So I draw a finite sheet, but we pretend it keeps going. Okay? Alright. So what are the symmetries of this thing? Well, the thing you can do with a sheet that doesn't change the setup is you can move it in any direction, like any sideways direction, like any horizontal direction. Don't move it up and down. That'll change things, right? But you can just move it sideways so that you can't tell. Like imagine I've got an infinitely large sheet of paper. There, I'm holding it close enough to the camera, it looks infinitely large. I'm now moving it. Right? Unless we reach the edge of the paper, you can't tell. Right? You can't tell. Similarly, I can rotate this sheet, like rotate it. So if I have a sheet of paper and I'm going to spin it, you can just maybe barely see it based on the fact that the paper isn't 100% smooth. Right? I'm rotating it. It doesn't change the setup. So those are my symmetries. So I want a surface, I want a Gaussian surface that it goes through my point, but it is also essentially matching those sort of symmetries. Now the way to do this is, in this case, I want to pick a box, and I want to make the box to have a height h above have its top surface, a height h above the sheet, and we're going to go the same direction below to keep things symmetrical. So I imagine again I have to draw this in 3D. Imagine I have a sort of box. I want to make it a rectangular box, but you could actually pick any shape of box. This is my top surface, and this point here is meant to be like part of the surface, right? It's like the sheet parallel to the infinite sheet of charge. It's hovering at a height such that the point where I want to find the electric field is right there, and then I'm gonna make it a box that goes down, and it goes underneath. It's really hard to draw. It hits the sheet, and then it goes underneath. Right, you can sort of see what I'm trying to do there. Right, this is where it hits the sheet. Then it's connected up underneath. Something like this. So it's like a big cube where I've got a certain top area A and the same area on the bottom. Right, and vertical sides. Now I made it a square, kind of something like it anyway. Rectangle of some form. Doesn't matter, right? The top shape doesn't actually matter. I'm just going to try to keep things simple. So the height of the cube would be 2h. H above the sheet, h below the sheet. What does the electric field look like? Well, could the electric field be at an angle? I'm going to argue it's going to go straight up or straight down. And if the sheet is positively charged, it's probably going to be pointing away from the sheet. Why can't it be at an angle? Why does it have to be straight up or straight down? Well, if it were at an angle, right, say from this point here, it's off to the side, then if you rotate your sheet, and remember that's one of the symmetries, then it would rotate the electric field would look different. than before, even though the charge distribution doesn't look different, right? The symmetry of the electric field would not match the symmetry of the charge setup. So electric field is going to be vertically up and vertically down underneath. And same thing over here, right? It's like that everywhere. Again, when I draw dotted lines, I mean like the lines are sort of like the hidden behind underneath the sheet. It's the best I can do here. Let me draw a different picture actually. Let me draw this from the side. Maybe that'll help a little bit. So imagine this is my sheet. This is my side view. We're looking at the sheet edge on, right? This piece of paper is my sheet. We're looking at it like this, right? Over the edge. In that case, I want to find the electric field up here, a height h, and I pick my surface to be this, where this is also h below, just to keep the top and the bottom symmetrical. I know I didn't quite draw it accurately, it doesn't matter. Same height above and below, and the electric field is this. Everywhere, of course, including where the surface is, but I'm not going to draw it there because it's going to be confusing. Okay. So the fact that the electric field can't point off to the side like this, well, that would violate the symmetry of my setup. So what is the flux? Well, if we are up here, the flux sticks out like this. If we're down here, the flux sticks out like this. If we're on the sides, the flux will stick out like this. And it doesn't matter what shape this is. Is it really, a rectangle on top or not? Could be a circle, then the flux will sort of stick out. Like it could be a cylinder, right? So, what is the flux through the surface? There's an area A on top of on bottom, right? So area A. And at the top and the bottom, the electric field is in the same direction as the should be a straight line. It's in the same direction as the area element, same direction as the flux. Right, so flux through top and bottom is going to be, and by flux through top and bottom, I mean, flux through a little piece dA. dA dot E. I know it's a different order from before. Remember, the order in the dot product doesn't matter. That's going to be dA times E, and E could be a function of height, right? Times the cosine of the angle between them. Well, the angle between them in this case is 0 once again, so this piece here is 1. What about the sides of the box? In this case, these rectangles on the side, but if it were say a circular surface on top, it would be the outside of that cylinder with some other funny shape. Doesn't matter, we just want vertical sides, they don't have to be flat. Whatever they are, it's going to look like this, right? The flux sticks out this way, the electric field is up, so those are perpendicular to each other. Bit like the ends of the cylinder in the last example with the infinite rod. Flux through sides. Well, we have the dA, the flux, is perpendicular, right? Perpendicular at 90 degrees to the electric field. So cosine 90 is going to come in equals 0. I mean, of course, I'm not implying that cosine 90 is 0. It's just a fact, but that is gonna feature in the flux. So no flux, no contribution to the total flux. because the electric field is parallel to the surface, therefore perpendicular to the flux. Okay. So then we have the total flux through our surface, our surface S, in this case our box, that is E dot dA. It's whatever E is, I don't know that, that's what I'm trying to find, times the area, in this case the area through which, only counting the area of the top and bottom, right, because I'm doing the integral, and the E comes out, it's constant. I guess I should put it like this. Where now, I guess it's no longer S, it's top and bottom, right? Because the flux through the sides that I would have to add to this to get the total flux is 0. Right? Okay, if you're confused right now, remember this. An integral is a sum. I want to find the sum of the flux over the entire surface of the box, right? And I have to include all the sides because it has to be a closed surface for Gauss's law to be true. But I can split up that sum into two chunks. The sum of the flux over the top and bottom, and the sum of the flux over the sides. But the sum of the flux over the sides is 0 because there is no flux. There is 0 flux, right? Because on the sides the electric field is parallel to the surface itself, therefore perpendicular to the flux. So therefore the sum of the flux of the whole surface is just the sum, is just the flux over the sum of the flux over just the top and bottom, because they're the only places where there is any non-zero flux. Then I can take out the electric field, which is constant there. Has to be constant because if it wasn't, if it would vary from one point to another, say if the electric field were a different value here from here, then that would violate the fact that this is meant to be symmetric under shifting left-right. Okay, so I hope you're clear why this flux ends up being this, where we just sum over the top and the bottom now. If not, pause the video, take a moment to think about it. So what is this area, right? So this is just the integral, meaning the sum over the individual area bits. Well, that is just the area. We write it out. Total area of top and bottom. Right? That's what this integral is. All I'm summing is the little areas itself, so I'm just going to get the total area when I sum them up. So that's EH times 2A. Because in the picture, the area on top is A, the area on the bottom is A. Okay, done, right? This is step 3. We figured out the total flux. Now we need a charge inside. Well, let's look at our box. It has vertical sides, right? So the area inside, let's see if I can color this a bit on here. This area here, this is the area that's inside our box, right? The wall sort of cut vertically down, so only that part is inside our box. So that itself has an area A. Area of sheet inside is just A. Oops, you can't see this. No, you can. Right. The sheet inside is just A. Therefore, the charge inside, the Q inside, is, well, how many square meters do I have times how many coulombs do I have per square meter, which is just what eta is, right? How many coulombs per square meter. Okay, so done. Now we can set them equal to each other. right? Gauss's law then states, and this is step 5, E H times 2A, that's the left-hand side of Gauss's law. Work this out up here. The total flux is equal to A eta, the charge inside, over epsilon naught. Don't forget the epsilon naught, epsilon 0. Okay, the A cancels out, right? That's good, because we made up our surface, right? We could have picked a different surface. We could have picked a bigger area here, or a smaller one, or a different shape. So what do we find? We find that the electric field, a height h from the surface, is given by the charge density divided by 2 epsilon 0. Notice it doesn't actually depend on the height at all. Right? We didn't know. We assume it might be a function of h, who knows? But we find that it's not. Right? There's just no... It's constant. If we go further away, higher up above the surface, electric field is constant, assuming it's an infinite plane. Right? That's the assumption here. In practice, it just means it's a large plane and we're fairly close to it. Right? So let me just draw this quickly. This is our final answer here. But like in reality, I might have like a large plane like this, and if I'm here, it looks, you know, it's large. It looks almost infinite. If I'm up here, I mean, this is I can clearly see the ends of it. Right, this point here, you can't really see the ends. They sort of disappear in the distance. More technically speaking, this distance here might be small compared to the size of the sheet, or the distance from the edges. Right, this is way smaller than this, whereas this height here is comparable to this. So, as long as you're close to the sheet, you can sort of pretend it's infinite, because it's just very large. That's kind of the application of these sort of infinite sized things. There's no infinite sized thing in real life, but there are things that get fairly close to it. Okay, so this is our answer. Alright. I'm going to leave it there for this video. It was a shorter one. I did manage to keep it a little bit shorter. In the next video, I'm going to do something that's somewhat more interesting, and it's probably going to take me a little bit of time. So, I'm going to put that in a separate video. I'll see you then.